So, good evening, everyone. Welcome to week 4 of Analog Electronic Circuits live problem solving session. I'm audible clearly, right?
Yes, yes.
Okay, so let's move ahead. So, last time we stopped at this problem where we had to find the DC operating point for this particular circuit, which is an CS amplifier. So, here, since all the values were given, we found out that VSDQ is 3.5 volts and ISDQ is 2.25 milliamperes. This is something we solved last time, right? So now what we have to do, so there were few follow-up questions based on this particular circuit. So we'll take up those questions first, then we'll move to the next problem. So in this particular circuit, so the first problem, which was a follow-up problem, was yeah. So in this particular circuit, you have to find the gain V out by V in. Assume the coupling capacitor C1 is shorted for input signal and select the correct options. So first question that arises is what is the condition for which your capacitor C1 will be shorted? What should be the condition that capacitor C1 will be shorted? Is it shorted for all the frequencies? By performing AC analysis, we simply put our capacitor to short, right? But is it true for all the frequencies? Coming from a practical perspective,
Because the impedance of the capacitor is basically dependent on the frequency. So at higher
yes.
frequencies, yes.
So Xc is 1 by omega c. So we have to make sure that omega is so high that your Xc almost tends to 0. So we have to keep this in mind. I'm not audible.
No, your voice is clear.
My voice is clear, right? Actually, somebody wrote that I was not clear. Mitish, can you check your speakers or settings once? I'm clear, right? Just in case if I'm not clear or voice is not clear, let me know. Or if I'm not audible. Okay? So, yeah, we were discussing that there must be certain frequency beyond which your capacitor acts as a short circuit. So, we have to keep this in mind that capacitor is not always short circuit, but it is short circuit at higher frequencies. But most of the times it is mentioned in the question that you consider your capacitor to be acting or your signal to be having certain frequency that makes your capacitor as a short circuit. Most of the questions you will come across this, or otherwise whenever we are performing AC analysis, generally it is considered that capacitor is short. But for those who are going for a practical application, you cannot consider your capacitor as short circuit always. So you have to keep this in mind that your frequency should be such that your capacitor is a short circuit. Okay, so yeah, with this we are going to move ahead, and in this simply we have to find the gain. So how do we find the gain of the amplifier, like gain of this circuit? What is the gain for CS? We know that small signal gain is GM into RD, right? And minus for the phase shift. We all know this, right? Now here Will it be simply GM into RD for this particular circuit, where this is RD? So the question is, first of all, let's draw the small signal model, okay? Source A, drain. Here you're taking
Gain
your
is GM into RD parallel RDS, right?
parallel.
RDS, small
Yeah,
r.
yeah. So you can consider like if there is, so here lambda was 0 in the previous question, right? So here since lambda is 0, so we don't have to consider the RDS. But yeah, so the question is, will it be simply GM into RD? So the answer is no. It will not be only GM into RD. Rather, see, when we say GM into RD, that means your amplifier only consists of this configuration, okay? Which RDS is present. So when we say that your gain is GM into RD, it is only for this particular configuration. Here your RD will also come in parallel. For this particular configuration, your gain is GM into RD, where your V in is actually VGS or VSG. Okay? But now, if you observe your circuit carefully, you will have these extra two resistors, right? Which are basically the bias resistors. So these two bias resistors will also come in parallel to your gate, and you will observe that the voltage appearing across your gate is not actually your input. So here it is like I1, R2, this 10K, and then you have your
Hmm.
this.
Yes, I think here the gain will be divided by two.
Sorry.
I think here, due to this configuration,
Hmm.
the gain will be divided by two.
Will it be simply divided by 2? Is it so?
Hmm.
Why it will be divided by 2?
Because VSG is going to be half of V input.
How? See, first of all, if this 10, so what is the importance that this 10 kilo ohm brings into this particular circuit? We have to understand that. Till now, we have seen the bias circuits which had only like gate biasing resistor divider circuit, right? What is new in this particular circuit? This extra 10 kilo ohms resistor. So what is it that this 10 kilo ohm resistor brings extra to this particular circuit? That is what we need to analyze. So here, let's say if this 10 kilo ohm circuit, 10 kilo ohm resistor was not present, so it would have been a short circuit, right? So your Vn would have actually appeared across your R1, R2 as well as your VGS or VSG, right? Is this clear to everyone? When I say this 10 kilo ohms resistor is not present, the voltage appearing across your VSG will be Vin. Is this clear to everyone? Because they are
Yes.
simply in parallel, right? Now what happens because of this extra 10 kilo ohm resistor? What it does is actually there will be a drop across this 10 kilo ohms resistor. After the drop, whatever the voltage you'll see over here will actually be, so this voltage will be parallel to all your resistors R1, R2 as well as your VSG, right? So the voltage now coming at this particular point will be your VSG, and which is definitely not your VN. Is this clear? So now when you go and solve for VSG, what will be the value of VSG that you will get? So it is R1 parallel R2 upon R1 parallel R2 plus 10 kilo ohms, right? So the equivalent circuit that we'll see is VN 10K, and it is like the combination resistance of R1 and R2, and the voltage that we are talking about is this VSG, right? So it appears as 10 kilo ohms is in series with this combination of R1 and R2, and here Vn. So now your VSG is actually R1 parallel R2 by R1 parallel R2 plus 10K into Vn. Is this clear to everyone how we got the VSG? Yes, any doubts in VSG? Okay. So basically, when we say V out by VSG, it is GM into RD. Sometimes this VSG is actually your Vin, so your gain remains GM into RD. But in this particular case, as we have already observed, our VSG and Vin are not equal. So for this particular case, our V out by Vn is GM into RD into R1 parallel R2 upon R1 parallel R2 plus 10K. Is this clear to everyone how we arrived at this particular formula? Any doubts with this formula? Yes. Okay, how many of you got this formula? Can you raise your hands? Okay, so out of 14, only 3 got it. What about others? Is this formula very difficult to understand? Okay, maybe Nitish. Nitish, you had this hearing problem, right? So is it audible right now for you? Nitish, am I audible to you? Okay, only few of you have got the answer, like got this. Others, is there any difficulty in understanding? Like, where are you unable to follow? See if you could respond, so we can go ahead, or whether we have to reiterate it. I'll get an idea. So here we have simply used the voltage division, right? Because of this extra 10 kilo ohm, there was extra voltage drop which was appearing. So that's why we use the voltage division and then the simple GM into RD. Okay. So since it is clear, so now we have to simply substitute the values of all these GM, RD, R1, R2, and we'll get the gain. Yeah. Now, first thing first, GM. So, how do we find GM? What is the formula? VSG minus mod VTHP, right? This is the formula for GM. We have the values 0.5 minus 1, which was VSG. The VSG that we got last time was 4 volts. So VSG is 4 volt, 4 minus 1. So GM is 0.5 milliamps into 3. 1.5 millisiemens. So we got GM. Then RD was given. Already it was 2 kilo ohms. RD is 2K. R1 parallel R2 will be 10 kilo ohms, right? 20 parallel 20. So it will be 10 kilo ohms. And your V out by V in will be 1.5 millisiemens into 2 kilo ohms into 10K by 10K plus 10K. So V out by V in is 1.5 millisiemens into 2K into 1 by 2. So it is 1.5. What is the unit?
The gain
Unit
is
is
unitless.
volt by volt, right? So unit is volt by volt. And what about in decibels? What will be the value that we'll get in decibels? Yeah, 10 log 10, 1.5. How much is this in dBs? What is the gain in dBs? Yes, come on. How much is it? 1.76? 1.76 dBs, right? Yeah. So moving on to the next problem with the same circuit. Here we have to find the input resistance that is seen by this particular circuit, considering that C1 is shorted. So what will be the input resistance seen by the circuit or seen by this voltage source? Input resistance seen by the input signal source. So how does the input signal source with the resistors look like? Vn 10K, 20K, 20K. So what is the resistance Zn that is observed from this side?
20 kilo ohm.
20 kilo ohm?
Is it 20 kilo ohm?
Yes. So it is Zn will be 10k in series with 20k parallel 20k. So that is 10k plus 10k 20k. So the Zn is 20 kilo ohms, right? Yeah. Now moving on to the next problem. In this problem, you have again got this particular circuit. Here R1 is 60 kilo ohms, R2 is 20 kilo ohms, RT is 2 kilo ohm, VDD is 12 volts, kW by L is 1 milliamperes per volt square, VTH is 1 volt, it's an NMOS. And what type of configuration is this? What amplifier configuration is this?
Common source.
Yes, it is common source, CS amplifier. Because gate, drain, source. So this is a common source amplifier with these particular components. We have to find again the voltage gain. Now here what will be the formula for voltage gain in this new circuit?
Minus GMRD.
Minus Gm into Rd. Right? Because whatever voltage that you are applying, it will directly drop across your VSG or VGS. Right? So in this particular case, we have to simply find the values of Gm, Rd, and we'll get our gain. So what is the first thing that you'll find from here? See, what is Gm? Gm is Kw by L, VGS minus VTH, right? So the moment we know VGS, we'll get the value of Gm. So what is VGS? VGS is
VGS equal, yes.
R2 R1 plus R2 into VDD.
Mhm.
So it is 20 by 60 plus 20 into 12. So which is 2 by 8 into 12, 4, 3 volts. So VGS is 3 volts. Now since VGS is known, so your GM is 1 milliamps per volt square into 3 minus VTH is 1. So GM is 2
2 millisiemen.
millisiemen.
Mhm.
RD is given. RD is how much? 2
2
kilo
kilo.
ohms. So your gain is
4.
4 volt by volt. Or if we talk about in dBs, how much will it be in dBs? How much will it be in dBs? Six. Yes. 6.02 dBs. So this is clear, right? Very basic problem. Just if you have any questions, don't write in chat, rather unmute yourself and ask, okay? Because I'm not keeping the track of chats. So I have not opened the chats yet. So better you unmute and ask, okay? Now moving on to the next problem. So in this problem, we have to find the input resistance for the circuit given. So yeah, for this particular circuit, what will be the input resistance? For this particular circuit, what is the input resistance considering that the capacitors are shorted? So what will be the input resistance seen by your input signal source? What will be the input resistance when you observe from your input signal source?
R1 parallel R2.
R1 parallel R2. Parallel? Anything? Parallel infinite we can write, because considering
Yes.
RG is infinite. So yeah, it is
Mm-hmm.
R1 parallel R2. So that is 60 parallel 20. So Zn is 15 kilo ohms.
Mm-hmm.
Now moving to the next problem. So in this problem, again for the same circuit, we have to calculate the output impedance. So first of all, what was the value for lambda? So here lambda was 0. So when lambda is 0, what does it tell you? Yes. What does
Pardon?
lambda
Can you please
what does
repeat?
lambda equal to 0 tells you about? What is lambda equal to 0 mean?
No dependency on VDS and under RDS equals 0.
RDS equal to 0, right? So yeah, we know that RDS is 0. Now in this particular problem, it is asked that what will be the output resistance of this particular circuit. So what will be the output resistance? So if we make
R drain.
sorry, what will be the output resistance?
R drain.
R drain, yes. So it is like drain source, where source is grounded. We know that there is no like uh, RDS is 0. The only resistance that we see here is R drain. So is it RDS equal to 0 or RDS equal to infinite? GDS is 0. So yeah. So lambda equal to 0, does that mean RDS equal to
RDS
0
infinity.
or
Infinity.
GDS equal to 0?
GDS equal to 0, RDS equal to infinity.
Yes, lambda equal to 0 means GDS equal to 0, not RDS equal to 0. Because if RDS would have been 0, your Z out would actually be 0, right?
Yes,
Because
yes.
0 parallel anything is 0.
Mm-hmm.
So RDS is not 0, rather GDS is 0, making RDS as infinite.
I like this.
Right. So your Z out will be infinite parallel RD. So we'll have RD, which is 2 kilo ohms. Yeah. So most of the circuits in these amplifier circuits, the major figure of merits that you have to calculate are gain, input resistance, output resistance. And as we move further, we'll talk about poles. So there, sorry, was somebody saying something?
No, no, no. Sorry.
Yeah. So the figure of merits that come into picture while considering these amplifiers are gain, input impedance, output impedance, as we have talked earlier as well. And as we move further, we'll talk about frequency responses. So there, the concept of poles and zeros come into picture. So poles and zeros are also something that are majorly considered in the figure of merits. Bandwidth will also come into picture. So these are the few things that you have to calculate when you are given a particular amplifier circuit. Okay, so it is very important. So whatever the circuit is, the concept always remains the same. You have to basically solve the maths depending on the circuit. But majorly, what are the main things or main figure of merits that you have to calculate for the circuits are all same. It is gain, input output impedance. Then when we go into frequency domain, so we talk about poles and zeros and bandwidths. So these are the few things that we have to calculate. So yeah, with this, let's move on to the next problem. So in this problem, uh, it corresponds to the same circuit again. Let's read this problem. So what it says that find the value of signal coupling capacitor C1 such that the lower cutoff frequency of the amplifier shown in this particular figure is 10 Hertz. So it is given that cutoff frequency is 10 Hertz. So you have to find the value of C1. Okay. So when it is given that the frequency is 10 Hertz, so frequency is represented as 1 upon 2 pi RC. Okay. So frequency is 1 upon 2 pi RC. At this particular point, what is your R? R is actually combination of these two with your Zn. So with your Rg. So that is Zn. So R is Zn into C1. So C1 is 1 upon 2 pi Zn into F cutoff, which is 1 upon 2 pi into how much was the Zn? How much was Zn? 15 kilo.
10 kilos, 10 kilos. Yeah. 10 or 15 kilos.
15 kilo into 10 hertz.
Yes. Uh-huh.
So what is the value of C1 that you are getting? Let me know with the units as well, okay? Yeah. What is the value of C1? Is it some value close to 1? But let me know the unit, like what is the unit that you are getting? Is it nano, pico, micro, milli?
Micro.
1 micro, right? So the capacitance value that you are getting for 10 hertz.
1.06 microfarad.
How much?
1.06 microfarad.
1.06, right? Close to 1. So 1 microfarad. Now let's analyze the circuit a little bit. Let's say your input frequency remains 10 hertz only. Okay. Now, for example, if I have used my C1 as 1 millifarad capacitor and I have used my capacitor value as 1 nanofarad, what will happen in the case of C1 being 1 millifarad? Yeah, if C1 is 1 millifarad, then what will happen? And what will happen if my C1 is 1 nanofarad? So we have found out that for 1 microfarad, the cutoff frequency that turns out is 10 hertz, right? Now I'm saying the frequency remains constant of your Vn. We are changing the capacitors. So what is the behavior that we will observe? in case of 1 millifarad and 1 nanofarad? Yeah, come on. What will happen in case of 1 millifarad?
Cutoff frequency changes.
How much will be the cutoff frequency? Will it be higher than 10, lower than 10?
Higher than 10.
So cutoff will be higher than 10. Okay, F cutoff is greater than 10 hertz. So what will happen? Your signal is 10 hertz signal. Your cutoff frequency is greater than 10 hertz. So what will happen? Will there be any change with respect to your signal that you'll see at this
I
particular
think it
point in this?
should be lower than 10.
Sorry, I could not get you.
I think it should be lower than 10, not higher than 10, because we increase the capacitance, and by increasing the denominator, the frequency will decrease.
Yeah. See, here it is milli, you had micro. So milli is actually larger than micro, right? So the frequency that you're seeing will actually reduce. This cutoff frequency will actually reduce. So your cutoff frequency is less than 10 hertz. Is this clear? I don't know who answered earlier. I didn't see the names. But yeah, is this clear to you? Like frequency will actually reduce, it will not increase. Because your denominator has reduced, right? Sorry, your denominator has increased, right? Here. So when you are increasing your denominator, your actual whole value will reduce. So your frequency will reduce. Is this clear? I don't know who answered earlier. So yeah, the frequency is reduced and it is less than 10 hertz. Your cutoff frequency is less than 10 hertz. So what will happen in this particular case?
In case of nano,
Cutoff.
the frequency will increase. The
Sorry?
cutoff frequency will increase. In case of nano,
Nano,
uh,
yeah. So it is opposite,
nano
right? So
capacitance.
for nano capacitor, the frequency would increase. So what I'm asking is, what will be the impedance? What will be the consequence of this cutoff frequency reduction or increase? Like, how will it affect your circuit analysis? So if your cutoff frequency is less than 10 hertz, then what will happen? If your cutoff frequency is greater than 10 hertz, then what will happen?
If it's greater, nothing will happen.
If it is greater than 10, nothing will happen.
Yes, if the cutoff frequency is greater than 10 and your input is lower than this cutoff frequency, nothing will happen.
Okay. So you are talking from low pass filter perspective, like this.
Yes.
So you are talking from this perspective.
Yes.
Okay. So if your frequency is same 10 hertz, your capacitor is 1 milli, we are saying that F cutoff has reduced. It is less than 10. So what will this capacitor do? Will it let your signal pass completely or will it block? So will you see the effect of XC or not? That is what I'm trying to ask you. So what is the importance that you'll see? So if XC tends to zero, if XC tends to zero, then it is completely short, right? So you won't see any drop across these points. Now if XC is not equal to zero, then we'll start seeing the drop. So here what we are saying is that for 1 millifarad capacitor, the cutoff frequency is lesser than 10 hertz and your signal is 10 hertz signal. So what will happen? Will your capacitor let this pass or will it block it? Simply you'll solve Xc, right? 1 upon omega c, right? 1 upon 2 pi into 10 into 1 millifarad, and Xc is 1 upon 2 pi into 10 into 1 nanofarad. So what will be the Xc that you'll be seeing in both the cases? Xc1, Xc2. Xc1 is lower than Xc2, right? Am I clear? So what will happen is, since your Xc1 is less than Xc2, that means in case of 1 millifarad, your signal will pass properly. The 10 hertz signal will completely pass through your capacitor, considering it will be a short circuit. But when you have a 1 nanofarad capacitor, at that particular case, your Xc is higher, your Xc increases, which will actually lead to a certain drop across this capacitor. So it will not act as a perfect short circuit. Am I clear? So did you understand what I mean?
Can you please repeat once?
Yeah. So see, what we said that we are changing the capacity. We are fixing the input signal frequency to 10 hertz, right? We are changing the value of C1 to 1 millifarad and 1 nanofarad. We have found out that for 1 microfarad signal, your signal passes properly, and it was mentioned in your question as well that it appears as a short circuit. So it allows to pass that frequency for 1 microfarad. Now the next question is, okay, let's change the values to 1 millifarad and 1 nanofarad, right? So here for 1 millifarad, what is the Xc that you will see? Yeah, what will be the Xc value? Xc1. And for 1 nanofarad, what will be the Xc value? Let Xc go. Let maybe quickly calculate. So it will give us idea 2 pi into 10 into 10 to the power minus 3. So it is 15.91 ohms. Now in the place of 1 millifarad, if I have 1 nanofarad, my resistance, that is Xc, impedance increases to 15.91 mega ohms. Can you see the difference? So here it is clearly evident that the resistance offered by 1 millifarad is much less than 1 nanofarad, right? And also that same thing is evident from this F cutoff analysis as well. So when your cutoff frequency is less than your 10 hertz like input signal frequency, your signal will pass through the capacitor easily. But when your cutoff frequency is higher than your input signal frequency, your signal will actually not be able to pass through your capacitor. So your capacitor will start blocking your signal. That is what we
Mm-hmm.
can observe from both the analysis, that is F cutoff analysis as well as your impedance analysis, right?
Mm-hmm. Mm-hmm.
So is this clear how things change when you change your frequency, or when you are fixing your frequency and changing your components? So
Yes,
that is
yes,
what
yes.
I mentioned, that you cannot always consider your capacitor to be short circuit. when we perform AC analysis in signal in circuits, we simply say that our capacitors are short. But that is not the case always, and these problems appear or come into picture into light when we are actually performing practicals in labs. That it is very important to actually calculate your cutoff frequencies and check which capacitor will work for you, which resistor will work for you. That is very important. So that's why. So this is what actually I wanted to highlight in the very beginning when I said that capacitor is not always shorted. So is this clear? Any doubts like what we were doing here for and how things changed when we have changed the capacitor from milli to micro to nanofarad?
Yes, super clear. Thank you.
Clear, right? Yeah. So let's move on to the next problem. So in this problem, we have to find the power dissipation of the amplifier, including the bias circuit. Okay. So first of all, in this particular circuit, did we calculate the current in this circuit ever? The current flowing through the amplifier?
Yes, I
No,
think so. I think.
we never calculated, right? Yeah.
Yes, we
So
calculated for the first one only.
yeah, so we have not calculated currents for this particular circuit. So first of all, it
Mm-hmm.
says like power dissipation needs to be calculated. So there will be
Uh-huh.
one current flowing through this particular path. So I'm naming
Uh-huh.
it as I1. And there will be another current flowing through this path, which is I2. Now, can you tell me like how to calculate I2? Like what can we find in what is I2?
I think this is IDSQ.
Yes, IDSQ. Because whatever the current that is flowing through your transistor will flow through this whole path, right, from VDD to ground, since they are in series. So your I2 is actually IDSQ. And I1 will be, how will we find I1? How will we find I1?
I1 is VDD over R1 plus R2.
R1 plus R2 because there is no current flowing through this path, right? So they are in series. I1 is VDD upon R1 plus R2. So we have to simply calculate the values for IDSQ and I1. So IDSQ, how do we find IDSQ? KW by 2L VGS minus VTH whole square. So KW by 2L, it was already mentioned. Yeah, KW by L is 1 milliampere per volt square and VTH is 1 volt. 1 by 2 milliampere per volt square. VTH is 1 volt. And what was the value of VGS that we got? It was 3 volts, right? What was the value for VGS? Yeah, 3 volts. So VGS is 3 volts. So IDSQ is 1 by 2 into 4 milliamperes. So IDSQ is 2 milliamperes. I1 is 12 by 60 plus 20 kilo ohms. So that is 12 by 80k or 80 milliamperes 43.15 milliampere. I1. So what is the how do we write power dissipation? What is power dissipation?
V times I. VDD times the current drawn from the supply.
VD into current drawn by the supply, right? I1 plus I2, which is 12 into 2 plus 0.15 milliamperes. This is volts. So the power dissipation that we get is how much? 25.8 milliwatt. Yes. So, okay, we have considered VDD and I1, I2. Why didn't we consider VS?
Pardon, can you please repeat?
Why didn't we consider VN? This is also a voltage source, right? It will also provide some current, will have some power drawn from this particular source. Why didn't we consider this?
I don't know, but I think because it is very low.
Yeah, we can say one reason is that because it is very low. And the main reason is that when we talk about power dissipation, it is the power drawn from the supply. We only when we
Mm.
say power dissipation, it is the power that is drawn from the supply. So we don't consider other sources. So only the supply is considered, and whatever the power that we are drawing from the supply comes under power
Mm.
dissipation. So definitely there will be some current I in, right, that will be provided by this source V in, and it will give rise to
Mm.
some power P in. But we don't
Uh-huh.
consider this in power dissipation because power dissipation is only with respect to your source. So whatever
Mhm.
power you are drawing from the source comes in power dissipation. Hope this is clear.
Whatever the power drawn from the supply, right?
Supply, yeah, from the
Yes.
supply or your VDD.
Yes.
So that is
Yes. But
only
I have
what
a
we call.
question here, ma'am.
Yes.
If we consider this reason, why we are not considering the power dissipation due to the signal swing, due to the small incremental current passing through
Yeah,
the
yeah.
the drain to source. Yes, it is
So that
also
is what.
drawn from the supply.
No, this V in is different. This is not a part of supply. This is
No,
different.
no, no. I am not
But
talking about
yeah, yeah,
in
I
the.
understand. So you are saying, so there will be certain increment, plus minus increment in your I1 and I2 with respect to your input signal V in, right? So that change. So when we talk about power dissipation, it is the static power dissipation in DC condition. So
Mm,
that is a static power dissipation. No matter if you're applying any input signal or not, there will be a power dissipation, and we call it as like static power dissipation. So here, what we are considering or calculating is actually the static power dissipation, which will be constant throughout. Now, when you
mm,
apply your signal, with respect to signal, your ID definitely changes, right? There might not
mm.
be any change in your I1, but your ID, your I2 will definitely change, which will change your power
Yes,
dissipation. But whatever
yes.
that changes, that is dynamic and it changes with respect to your input signal. But the calculation that we are doing currently, it is static power dissipation and it will stay throughout.
Mm, mm.
So
Okay.
there will be an extra power dissipation which will be in form of this AC, which comes into picture because of your input signal.
Mm, mm.
That's why here we are considering all DC currents. So these are DC currents, right? I2, this current that we calculate, this is a DC current, right?
Yes,
Also,
yes,
this is a DC current. So yeah, so this is a static power dissipation. Clear?
yes.
Yeah. Okay. So any doubts? Any doubts? No doubts, right? So let's move on to the next problem. So in this problem, so the given circuit has again a P transistor with the DC bias current of 124 microampere. When it says DC powered DC bias current. What does that mean? What is DC bias current? Yes, what is the DC bias current of the MOS device?
DC bias current, I think IDS.
Yes. So in this case, it is ISDQ
Mhm.
since it is a PMOS. So 124 microamperes. It is mentioned that PMOS is in saturation, and the current equation that it follows is IDK VSG minus VT whole square. K is mentioned to be 3.83 millisiemens per volt. VT is zero point 0.5 volts. You need to work out for the values of R1, R2, RS, and RD such that the current through the potential divider R1 and R2 is zero point 0.5 microamperes. The current through MOS device is 124 microamperes. The approximate gain of the circuit is 5 minus 5, and the output can swing symmetrically over the largest possible range, which maintains the device in saturation. So now this is a new type of problem, right? We have never used this type of problem, but this is actually a practical problem that comes into your hand. So you have a MOSFET. So for that MOSFET, you know your values of W by L, Cox, mu, everything. So basically, the K is always known, right? Now, when you are designing an amplifier, so this is how you get the specs. And for that, you have to select your capacitors and resistors so that your like amplifier gives you the desired results. So this is how the design problems are actually made. So this is how the actual problem is in real life. So let's move on and solve. So first thing that is mentioned is your potential divider should carry zero point 0.5 microamperes of current. So current through your potential divider will be I1. Let's say if I say this is I1, it is VDD by R1 plus R2. Here VDD is given 5 by R1 plus R2, and this is equal to 0 0.5 microamperes. So from here you can get like the values of R1 and R2 to be how much? R1 plus R2 is 10 mega ohms, right?
Yes, yes.
This is clear, no? Now next is the current that is flowing through the MOS device is 124 microamperes. So whatever current that is flowing through the MOS device, that same current is flowing through RS and RD also, right? The current which is flowing through the MOS device, that same current is flowing through RS and RD, correct? Because they are in
Yes,
series.
yes. Mhm.
So if we write a KVL, so how the KVL will look like, it is 5 volts, then voltage drop across IS, so I into RS, plus drop across RD, so I into RD, plus this
Plus zero.
VDS or VSD, since it is a PMOS, so it is VSD, the drop across the transistor. Now, how do we write VSD? So here, in this particular circuit, and we also know the gain, so we can work out for gain also. So we can go by either ways. So maybe let's quickly start with the gain, because gain will help us out in many ways. So gain will add to our
From the gain,
solution.
we can get VGS.
Yeah, so what will happen? So here, this is one formula that stays true. Now here you have to find current, RS, RD, I, VSD, all these are unknown, and this is the only equation that we know, right? The next equation that we know is I equal to K VSG minus VTH. And I is known, K is known, so let's write it down, 124 microamps. K was how much? 3.83.
Sorry, what is
3.8.
I1, ma'am? What's I1?
ID.
Mm.
These are all ID.
But don't
Millisiemens
forget
per.
half mu NCox, half K,
Sorry?
half K, half K, half multiplied by K.
No,
This
no.
is the
So
current
here
voltage.
K is already mentioned. Like current is mentioned K into VSG. So you have to consider
Ah,
that K. If it was not
mm,
mentioned, we would have gone for KW by L, W by 2L. So here it is
mm,
already
mm,
mentioned the current formula, so we have to follow the same.
mm,
So
mm,
VT is 0.5. Now here V is G minus zero point 0.5. So in this
mm,
particular circuit, we have to find Vs and Vg. So how do we find Vs and Vg? So this is the circuit that we have. Here we have to
mm,
find the values for Vg, this and this point, Vs. No,
mm,
sorry, Vs is this, right? PMOS. So this is Vs. So these voltages need to be known.
mm.
So can we find Vg? Do we know the value of Vg? We don't.
I think okay.
Because R1 and R2 are not known. We know the value
Yes.
of R1 plus R2, but we don't know R1 and R2 separately. And
Mm,
similarly, we also don't know RS. So, and RD, we cannot find the values for VS as well.
mm,
So we have one equation, two equation, three somewhat there. Now we have used, what all we have used? We have used that this current. So what are the facts that we have already used? That this particular current to be 0.5, we have used that. This fact we have used. Swing, we'll try to see the swing at the very end. So swing comes at the end. We first compute everything, then we go for swing. So what is
mm,
left? So the left
mm,
figure of merit is gain. So we have to
mm,
design this circuit for a gain of 5 volt by volt.
mm,
Now let's quickly calculate the gain for this particular circuit. How the gain for the circuit look like. So uh, since it is
mm.
a circuit with both RS and RD, let's quickly draw its small signal model. Okay, source, gate, drain,
Excuse me,
plus
ma'am.
minus. Yes,
This equation 2, so here it
equation
should be BSG
whole
minus
square,
point 0.8 whole square.
whole square, right? हाँ
Yeah, yeah.
square miss हो गया था हाँ square GM IST and okay, since nothing has been mentioned about lambda, so let's consider that there is no lambda is 0. For now, let's consider that lambda is 0. So we don't see any RDS, small RDS. Now here RD, okay, this is grounded. So we can directly compute here as RD and source drain. There is another resistor which is there. So this is V out. This is not between source and ground. This is RD, which is separately grounded.
Source, there is a source resistance.
So there is this source resistor which is grounded from source. So here the source is not grounded because
Yes,
here this will be grounded, right? So when
yes,
this is
yes.
grounded, so this RS is there. So this is how we'll draw it here. So this source is not grounded since it is not directly connected to voltage. So RD, RS, R1 and R2. R1 and R2, so this will come here. R1 parallel, R2, and from here we are supplying the input. Yeah. Anything else left? Nothing left, right? We have covered all. Okay. Now here, first of all, VSG. So for this voltage, here this particular point that is VG is at Vin. So, and if we see our V out, which is at this point, and from this to ground is V out. So whatever current that is flowing through RD will provide a drop which will appear as V out. So again, V out is GM sorry VSD into RD. So that this
GMVSG.
GM VSG
GMVSG.
GM VSG GM VSG into RD. Yeah, GM VSG into RD is V out. So we have found out V out. Now here we know that Vs is this particular voltage, right? So how to write this voltage? This voltage can be written as this is Vs from this point to ground. So whatever the drop will be there across RS, that will give us Vs. Okay. And this current is flowing in this direction. So if I, and this is the only current that is flowing through in this whole path, right? From this ground to the other ground. So if I can write it as simply minus changing the direction into VSG into RS will give us Vs. Now Vs equal to minus Gm Vs minus Vg into Rs. And here we know that Vg is actually Vn. This is clear from here, right? So Vs equal to minus Gm Vs minus Vn into Rs. So Vs plus Gm Rs Vs equal to Gm Rs Vn. So Vs 1 plus Gm Rs equal to Gm Rs Vn. So Vs equal to Gm into Rs into Vn upon 1 plus Gm Rs. So we have found out what we have found out. Vs we have found out, and we know Vg equal to Vn. Now here we said V out is Gm Vsg into Rd, right? So V out is Gm Vsg into Rd. That is Gm. We'll substitute the values of Vs. That is Gm Rs Vn by 1 plus Gm Rs minus Vn into Rd. So how do we write gain? Gain is V out by V in, right? So we will simply take this V in common. So it is GMRS minus 1 minus GMRS by 1 plus GMRS into RD. These two cancel. So yeah. So V out by V in is
minus GMRD
GMRD, sorry,
minus GMRD
1
minus
plus
GMRD.
GMRS, and here a minus sign that comes from here. So we have GMRD by 1 plus GMRS. We know that GMRS in general will be higher than 1. This is always the case. GM into RS will always be 1. So for this particular condition, what will be the gain that we'll observe? It is actually minus GMRD by GMRS, which is actually minus RD by RS. So the formula of gain that we have got is minus RD by RS. Okay. So
Ma'am,
yes,
ma'am, I got a confusion in
yeah,
the V out formula.
yes, V out
So
formula.
V out we have written GM IST into
No, GM VSG, right? GM into
GM.
VS.
Oh yeah, yeah. Sorry. Okay,
Yeah,
okay, okay. Yeah,
GM VSG into RD,
yeah. Correct. Sorry.
right?
Yeah, yeah.
Yeah.
Correct.
Okay. So yeah, finally we have got that V out by V in is minus RD by RS. It was mentioned that V out by V in is how much? Minus 5, which is RD by RS. So minus RD by RS. So we found out that RD is 5 times of RS. This is clear to us. Now this is another result that we have got. So let's say 1, 2, 3. So this is 4. Okay. Now we have found a relation between RS and RD. We have found VSG. We have found out, right? No, we didn't find VSG, but V out is ID into RD. So we have this formula. ID is known to us. RS RD में we have found a relation. VSD is not known to us. Okay. So so for till now we have got these things. Now, okay, we have used everything, but still we are left with VSD, RD, RS, as well as R1 and R2. We are not clear with these values. So now what we know right now is final thing, that is swing, which is left. The condition for swing, and it was said that the swing should be symmetric over the largest possible range, and which will maintain the transistor in saturation. So when there is a so when there is this particular beautiful amplifier that we have, which is a CS amplifier. Here, when we apply some input, a signal and input, it will definitely change our ID, right? That is what we were talking about. Currently, what ID that is mentioned is IDC, which is 124 microamperes, which is mentioned. Now, earlier we were talking about how things will change when we have an signal, that is a AC signal, right? So that definitely it will introduce some ID, right? And what actually happens is these two are opposite in nature. So this node and this node are opposite in nature, 180-degree phase shift. So if I say my I total in this branch will be IDC plus small id, since these two are opposing in nature, so what happens is when Vn actually increases, your ID will reduce because they are 180-degree phase shift. So negative voltage that appears, right? So negative happens. So for the case of let's say a condition when your small v in is such that your IDC becomes this ID and this IDC both become equal. So the I total will actually be IDC minus IDC, that is 0. So I total will be 0. Now for the case when your V
Ma'am, can you
in,
explain that
so see how it happens
condition?
when there is a CS amplifier. So in CS case, your first of all the gain is negative. What does negative mean? There is a 180-degree phase shift. So when there is a like your if your input signal is like this is V in, the output that you will get will be like this. So you will see the amplification, but your phase is opposite. So what does that mean? It means that when you are applying higher voltage, so let's say this is also voltage, right? V out. So when you are applying like higher V in, you are getting lowest V out. मतलब negative में है ना? So it is lower. Like if we only talk about magnitude, the magnitude value is higher. But if we see in a scale from positive all the way to negative, for the highest input, you're getting the lowest output, right? And for the lowest input, you're getting the highest output, right? Am I making sense what I'm trying to say?
Yes, yes, yes.
So what happens is this is the DC value that we are talking about. So let's say your VDS, your VDS is fixed at this point. This is DC, which is a bias point that is always fixed, that we know. Now, what is happening when you are applying your input voltage? So, as your input is increasing, your output value is actually reducing. And when you are actually reducing your input and have reached your minimum, your output actually peaks and it increases to the top, right? So, here what happens is so that is what the condition that we are talking about. Like we are saying that let's say when V in reaches its maximum, what we are saying is that the current that we are getting is close to the IDC, but since it is the positive cycle, so the value will be negative. So they both cancel each other and we'll get a 0. Now for the case of V in reducing, that is for negative cycle, ID will increase, and the I total that we will get is IDC plus IDC that is twice of IDC. So this is the condition that we have considered.
Hmm.
Now,
Uh,
what is,
but,
sorry?
Shahd, yes, I have understand it till the point of the V input increase, V output decrease
Right,
because due to the 180 phase shift. But
right.
I'm not able to understand the condition of I total.
Okay, so how can we understand this? So, when we talk about swing, so swing is somewhat like this, right? And
Yes.
we are saying that we want a maximum possible swing.
Mm.
So, this is the swing that we are talking about. This is the DC bias point. Let's say IDC. Okay. So, what can happen is the maximum that we can go, uh, it's like if let's say it is DC, IDC, so the maximum that you can have this is like the value equal to the DC current, and the minimum, sorry,
Mm.
sorry.
No, no
Okay,
worries,
yeah.
no worries.
Yeah. So minimum trough that we can have in terms of current is also IDC. So these are the extreme cases that we can have. So there might be a condition for input such that for that with those particular oscillations your maximum current that you can achieve is actually IDC plus IDC, which is 2 IDC, or it can be 0 IDC, because this IDC and this will be like minus of IDC, right? So 0. These are the two extreme conditions which are considered. Now, for these extreme conditions, now what we are doing is we are trying to solve our equations. So, for the condition when IDC plus small id is equal to 0, that is this particular condition, this is one condition when they have completely opposed one another. There might be another condition when IDC plus small id is 2 IDC. 2 IDC. This will we will achieve this particular current when Vn is actually reducing. This we will achieve when Vn is increasing due to that 180-degree phase shift that I mentioned earlier, right? So now for the case when IDC plus ID is 2 IDC, in this case, when this is the current that we have, it is already mentioned that your transistor remains in saturation. So for this particular swing, your transistor should remain in saturation. So what is the condition for situation that VGS should be VGS minus VTH uh, is equal to VDS. This is what we know. VGS minus VTH should be equal to VDS, and since it is a PMOS transistor, yes, PMOS. So let's write it in terms of PMOS only. So we'll write it as VSG mod of VTH should be equal to VSD, right? This is what we know. Now ID is how much? It is K VSG minus VTH whole square. So VSG can be written, VSG minus VTH can be written as root under ID by K. So VSG minus VTH is root under here current K here. Okay, it is K VSG. So for this particular case, VSG minus VTH is root under ID by K. This is the ideal condition, but we are considering that your IDC plus ID, which is I total, is 2 IDC. For this particular case also, your transistor is in saturation. So for this particular case, if the transistor is in saturation, that means your VSG minus mod VTH whole square K equal to 2 IDC. So this is the current that is flowing through the whole path. So that path current is equal to K VSG minus VTH whole square. So VSG minus mod VTH is equal to root under 2 IDC by K. So this is the value of VSG minus VTH. Okay. So, and this is also the value for VSD. This is also the same value for VSD. Now, when we look into this particular circuit, the same circuit, for the same circuit, we know VSD, IDC is already known, K is known, everything is known. So now here, let's say I'll write the same KVL again. So the KVL is 5 equal to IDC RS or IDC RS plus, or we can write any formula. We can write it like V out के respect में we can write, or we can write it like VSD. Let's say VSD equal to this VSD is 5 minus IDC RS plus RD, right? So we know IDC, RS, RD में we have this relation, and we know VSD. So we can find our RS and RD from here. So Vs is 2 IDC by K root under equal to 5 minus IDC into RS and RD. RD is 5 times RS. So RS plus 5 times RS. So from here we can find a RS. So RS is 5 minus root under 2 IDC by K by 5 IDC. So the value of RS that we get is 3.189 kilo ohms. The value of RS that we get is 3.189 kilo ohms by solving this particular equation. Now since RS is known, the next question is what is the value of RD? So RD is 5 RS. This is 5 times of 3.189 kilo ohms. So your RD will be how much is this? Like 3.2. So 3.2 is 7 kilo ohms. Oh no, 5 so it is 16 kilo ohms. 16 kilo ohms is your RD. The next problem is values of R1 and R2. Now for values of R1 and R2, what all we know? We know that VSG minus VTH is VSG minus VTH is root under 2 IDC by K. Okay, here. And R1 plus R2 is 10 mega ohms. Yeah, 10 megohms. R1 and R2 is
Excuse
10.
me, ma'am.
Yes. Yes.
Ma'am, in that formula, if we substitute all the values in the
Ah.
RS formula above,
Yes,
we are
yes.
getting the answer as 6.345.
6.345.
Yes, ma'am.
So, okay. So, you're getting RS as 6.345.
Yeah,
But,
double of
okay,
the
okay.
answer that we got.
Right, right. Yeah, see. Now, here we have considered the case when your total current from this particular path, I total, is 2 IDC, right? So, the current that is flowing through each resistor RS as well as RD is also 2 IDC, right? Correct?
Okay. Okay,
So,
ma'am.
here actually there should be a factor of 2 into 2.
Okay.
So, now are you getting the correct answer? That's why I didn't mention it there. See, when the current we are considering, which is flowing through this particular path, is 2 IDC. So that same current is flowing through your resistors also, right? So whatever the current we are considering for VSD, that current needs to be considered for these resistors also. So that 2 should be there. So yeah. So this 2 is important. Let me highlight this. Now the reason for this 2 is actually the conditions that we have considered. Because of this 2 IDC, here also we will get 2 IDC. And that's why the RS that we are getting is 3.189. So, yeah. Now we are at this point. So, R1, R2 is known. VSG is root under 2 IDC by K plus VTH. 2 IDC by K plus VTH. So, what is the value of VSG that we are getting from here? Root under 2 IDC by K plus VTH. VTH was, I guess, 1 volt. 0.5 volt. 0.5 volt. 3.83, 0.5, 124. Yeah. So this is the condition for 2 IDC when Vn is low. Now if we consider the same formula, then the value of VSG that we will get is 2 into 124 microamps by 3.83 milliamps per whole square plus 0.5. So the VSG that we are getting is VSG that we are getting is 0.75 VSG. This is the VSG that we are getting. Now for this VSG, VG is R2 by R1 plus R2 into VDD. VS is, this is VS. So VS is 5 minus IDC into RS. Now here one thing. So if we are considering 2 IDC here, then definitely we have to consider 2 IDC over here as well, right? For the uniformity. In this formula, if we are considering 2 IDC, then here also we need to consider 2 IDC. If in this formula, if we would have considered only IDC, considering the DC case, then here we will also get the IDC, DC case. Am I clear? The results will fluctuate a little bit in both the cases because of this extra factor too. But let's solve in both the cases and check like how much is the difference that we can actually see. So we have already found out uh, IDC is given, RS is known. So we can find VS. VS we will find VG. So how much is the VS that we are getting? 5 minus 2 into 124 micro into RS was 3 point, how much? 3.182, 3.2 kilo ohms. 3.2 kilo ohms. So VS that we are getting is 5 minus 2 into 0. 4.2064. 0.2064. So VS minus VG is 4.2064. So VG is, no, 8.75. So VS minus VG, VG is VS minus 0.75. VG is 4.2064 minus 0.75. 3.4564. So 3.4564 is equal to R2 by 10 mega ohms, we already know, into VDD is 5 volts. So R2 is equal to 3.4564 by 5 into 10 mega ohm. So R2 is, let's say if it is 3.5 into 2, so it's around 7 mega ohms. R2 is around 7 mega ohms and R1 is around 3 mega ohm. Is this clear how we solved this?
Ma'am, can you please repeat after this? VS is 5 minus 2 IDC into RS. We are considering for 2 IDC.
For 2 IDC, yes. Because here what we did when we were calculating VSD, here we considered 2 IDC, right?
Mm-hmm.
Otherwise, in general, what is the formula? ID is K VSG minus VTH whole square, right? So if we go around with this formula, what we will get is ID by K root under is VSG minus VTH. If we go by this formula, we'll only see one IDC.
Yeah.
But here we are getting 2 IDC because we are
Right.
considering that 2 IDC condition जो VN के साथ था. But ideally, what I would say, so this I have solved to consider that 2 IDC condition. But generally, when we are finding the values of resistors, we can go by only using one IDC condition. So instead of going for 2 IDC, if we would have gone for one IDC condition also, that would be correct. Because we are trying to get the this right. We are trying to get the value of resistors, and resistors are like mostly they are for DC biasing. So especially R1 and R2 are used for DC biasing. So we need not to go for this 2 IDC one. I just solved with this, so this is another way we can go around, but it will definitely change the values. We'll see the fluctuation in values. The values won't be same. And uh, yeah, because this extra factor of 2 is coming into picture, right? So because of which we'll see the fluctuation. So if 3.4564 into 2, I'm getting it is 6.9128 I'm getting. And here, so because of this, what I am getting is 6.9128 mega ohms. 6.9128 mega ohms, and the remaining R1 is 3.0872 mega ohms. This is the result that we are getting considering 2 IDC. So let's write down. Now let's see if we solve using IDC, how much is the difference that we are getting. So this is with 2 IDC. Now considering IDC, if I solve, then your VSG minus VTH is equal to under root IDC by K. So VSG is under root IDC by K plus VTH. Vs is equal to 5 minus IDC into RS. So Vs is equal to 5 minus 124 micro into 3.2 kilo ohm. So it is 5 into 3.2. So Vs is again 4.6032. If Vs is this much, VSG is root under 124 by 3.83 minus 3 plus 0.5. So root under 124 into 3.83 plus 0.5. This is 0.6799. So 0.68 ले लेते चलो, and 68 volts. So VSG is this much. So VG will be Vs minus VTH, that is 4.6032 minus 0.68. So 4.6032 minus 0.68. VG is 3.9232 volts. So R2 is 3.9232 into 10 mega by 5. So this is 7.8464. 7.8464? The options may be something is wrong. कहीं कोई कैलकुलेशन मिस्टेक है क्या? 3.2 ही था. Okay. The value that we get. How much is the value that we are getting for this? 0.124 by 3.23. This is 0.1799. 1.799 or 0.5. 0.6799. Yeah, so by solving this, the values that we are getting are 7.8464 mega ohms, and जो remaining होगा R1 का, that 2 mega ohms. So that is the value that we are getting. Now, okay. So this is the difference that we are getting when we are solving using 2IDC or IDC. This 2IDC condition, we have got the values as 6.9128 mega ohms or 3.0872 mega ohm. While considering only IDC, the values that we are getting are 7.8464 and 2.1536 megaohms. So these are the two set of values that we are getting considering 2IDC and IDC. Is this clear? It is solved both with both ways. Okay? Considering 2IDC also and considering IDC also. But ideally, because these are resistor values or resistors, they are generally used for DC biasing. और ये जो current होता है, it is already fixed. So I1 के across this path, the current does not change. It is always DC. So better we consider IDC one only, like rather than going for 2IDC, which was the condition with signal. So rather than that, if we can solve the resistor values with only DC currents, then it is better. So here also, rather than going for 2IDC, we can only solve using IDC. So that will also be. Is this clear? Any doubts? Yes, close to 8. Did you understand the argument that we had right now? Like why we solved for two different cases? What is this 2IDC? Why we get IDC? All these things, are they clear to you? Any doubts? Any doubts in the group chat? Let's check the chat. Okay, there are no questions in chat. So did you understand the arguments that we had, like why we are using 2IDC, where to use IDC only, how things change when you change, like when you are using 2IDC and when you are using IDC. That's why I performed this calculation using 2IDC as well as IDC both. So are this clear to you? Am I audible? Hello? Hello? Am I audible to everyone? Okay. So are these arguments clear to you? If you have any doubts, please ask. No doubts? Is this clear to everyone? Maybe we can stop over here. We have solved 12 questions today. Maybe we can move ahead in next session if there are any problems. If you don't have any doubts, maybe we can. Previous, which one? This problem? Problem number 6. Okay. Nitish, can you unmute? Maybe it will be convenient. 6. Problem number 6. Yeah, this is problem number 6. Yes. What is the doubt over here? What was the doubt in this particular question? Question number 6. What is the doubt? You're muted. I'm unable to hear you. Z out. Oh, okay. So, see, when we make a small signal model, this is how the output side looks like, right? So we have GMVGS, RD, and let's say we will have some R0 over here. But in the question, it was given that lambda is 0. Lambda is 0, that means the slope that we talk about in practical scenarios, the slope is 0. So if lambda is 0, that means your GDS is 0, which is ID by VDS. So R0, that is VDS by ID, is infinite. So that's why there was no R0 in picture, and the only Z out that we see from this output, this was the output node, right? So from this output node, the R out that we see or Z out that we see is only RD. So that is Z out. That's why we have written Z out as RD. Is this clear? Okay. Any other doubts? Okay, it's already 8 p.m. So if we don't have any further doubts, maybe we can break over here and meet next week. So thank you, everyone. Have a wonderful evening ahead, and let's meet next week again. See you. Bye.
Thank you. Bye.
Thank you. Bye. So I'll upload this video immediately on YouTube, and maybe if you have any doubts further, also you can comment in YouTube or like in the comment section, or you can come up with that doubt in the next session, and we can discuss it again. Okay, hope that works. We'll see you all next week. Bye. Good night.